So for number 5, we want to prove that the natural number x is prime if and only if x is greater than 1 and there is no positive integer greater than 1 and less than or equal to root x that divides x. So this is a biconditional statement, and that means that we have to prove p implies q, where this one, this is p, and that, and this is q. And we have to prove that q implies p. So we have to do a two-part kind of proof. So let's begin with part 1. We're going to say part 1. We're going to say assume that the natural number x is prime. So we're going to say let x belong to the set of natural numbers. And we're going to say suppose x is prime. So if we suppose that x is prime, then by definition it means that x, then by definition x has only 2 factors. X and 1 with x being distinct from 1. So if x is distinct from 1 and x is a natural number, therefore it means that x is greater than 1, right? If it's not 1, it has to be greater than 1. And x cannot be 1 because by definition, if the number is 1, then it's not prime. So if x is greater than 1, we're going to just square both sides. So we're going to say x squared is greater than x. And now we're going to, not square, multiply both sides by x. And now we're going to square both sides. Take the square root. So now we're going to say that x is greater than root x, because we multiplied both sides by x, and now we're just taking the square root. So because x is greater than x, and x is not equal to 1, therefore our conclusion is going to be, therefore x is greater than 1, and there is no positive integer greater than 1 and less than root x, and less than or equal to root x that divides x. So we've done part 1. Now we're going to do part 2, where we assume q and show that it leads to p. So let x be greater than 1 and suppose there is no positive integer greater than 1 and less than or equal to square root of x that divides x. So we begin by assuming, well, my handwriting's trash, but we begin by assuming q, right? And what we're going to do here, let me just improve this because this is so terrible. Greater than 1 and less than or equal to square root of x that divides x. Okay, so we're going to say, okay, let x is equal to n times n for positive integers m and n. So the reason that we have said this is because we began by saying here, let x belong to the natural numbers, right? So because x is a natural number, it means that it can be expressed as a product of two other positive integers. Okay, so once we're here, we're going to say let m be less than or equal to n without loss of generality. This without loss of generality means that the same reasoning is going to apply if you had assumed that n was less than or equal to m. It just means that we can take the same logic without having to prove both cases separately. And we're going to suppose this because if we have two integers that multiplies to x, it means that one is going to be equal to or less than the other. And so we've supposed this. So with this being said, we have that m is equal to 1 or m is greater than root x because of what we're supposing here, right? We're supposing that, hey, if m divides x and m is greater than 1, it means that m is greater than root x. So we have that m, so then we have the m squared. Actually, I'm going to say case 1, m is greater than root x. So in this case, we have that m squared is greater than x, right? But x is equal to m times n. So m squared is going to be greater than m times n. So if we divide both sides by m, m is going to be greater than n, which is a contradiction, right? This can't be because we assumed this. So we're going to say which is a contradiction. Which is a contradiction. So if it is a contradiction, it means that therefore m is going to be less than or equal to root x. So m must be equal to 1, right? It's the only value that m could have. Well, if m is equal to 1, then x is going to be equal to, remember that x is m times n, so x is going to be equal to 1 times n, so x is equal to n, right? Therefore x is equal to x times 1, so x must be prime. So x must be prime. And so we have shown the biconditional now because we did if Q implies P. So that is it for item A. This whole thing here, part 1 and part 2. Now let's do item B. I just have to erase all of this, and let me erase this more efficiently, I suppose. So erase that, and that. Okay, we are good. And now for part 2, we have that, actually item B, we have proof that P is a prime number, and if P is a prime number and P is not equal to 3, then 3 divides P squared plus 2. And we have to use the fact here, the hint that they give us, we have to use the fact that when P is divided by 3, the remainder is either 0, 1, or 2, right? Only 3 possibilities. So if it's, only these 3 possibilities. So let's begin working with this. So we're going to say, suppose that P is prime, right? So for item B, but actually I'm going to begin over here. Suppose P is prime and P is not equal to 3. So if P is not equal to 3 and P is prime, then 3 does not divide P. Well, if 3 does not divide P, it means that the remainder has to be 1 or 2, because if the remainder is 0, that means that it is divisible by 3. Then we're going to say, thus, when P is divided by 3, the remainder is either 1 or 2. That's the definition of it not being divisible by 3, right? So let's consider two cases. So we're going to say case 1, the remainder is 1. The remainder is 1. Is 1. So if the remainder is 1, it means that p divided by 3 is equal to k plus 1 over 3 for k belonging to the set of integers, right? So this means that I'm going to multiply everything by 3. So p is going to be equal to 3k plus 1. And now we want to get to p squared plus 2. So we're going to go that p squared is going to be equal to, oops, that was a different color. So p squared is going to be equal to 3k plus 1 squared, which is going to be equal to, that's going to be 9k squared plus 6k plus 1. So p squared plus 2 is going to be equal to 9k squared plus 6k plus 1 plus 2 plus 3. Now I'm going to factor out the 3. It's going to be equal to 3 times 3k squared plus 2k plus 1. And now we say, okay, 3k squared plus 2k plus 1 belongs to the set of integers. So what do we have here? Oh yeah, so p squared plus 2 is divisible by 3. So that is case 1, where we have that the remainder is 1, right? And so p squared is going to be equal to 9k squared plus 6k plus 1. And then when we add plus 2, it's going to be divisible by 3. Now let's do case 2. So case 2 is when the remainder is 1. The remainder, oh, sorry, it's 2. Is 2. So that means that p over 3 is going to be equal to m plus 2/3 for some m belonging to the set of integers. So then I have that p is going to be equal to, multiply both sides by 3, 3m plus 2. So p squared. Actually, let me make this a little bit closer. So yeah, p is going to be equal to, p is going to be equal to 3m plus 2. So p squared is going to be equal to 3m plus 2 squared, which is going to be equal to, let's see, that's going to be 9m squared plus 12m plus 4. And then we have that p squared plus 2 is going to be equal to 9m squared plus 12m plus 4 plus 2 is going to be plus 6, which is equal to, I'm going to factor out the 3 times 3m squared plus 4m plus 2. Okay. So once we're here, we're just going to say that 3m squared plus 4m plus 2 belongs to the set of integers. So p squared plus 2 is divisible by 3. So we have shown that in either case here, so that's the beginning, and then we have case 1 where the remainder is 1, case 2 where the remainder is 2, and in either case we have shown that p squared is divided by, p squared plus 2 is divisible by 3. So our conclusion is going to be, therefore, if p is prime and p is not equal to 3, then 3 divides p squared plus 2. Yeah, and that is it for item B.